In this final demonstration of the course, we're going to be looking at hypothesis testing and how we can use these tests to infer different results from our data based on models we create. In order to explain this, I'm going to run through an example. On screen, you can see two data sets. We'll call these deposit A and deposit B. At each of these deposits, we've measured the maximum grain size in millimeters for a set number of samples. Given this data, the sort of questions we might ask are, is the grain size higher in deposit B than deposit A? The reason we might be interested in this is that it would tell us whether the energy levels were different in both deposits or not. Now we can see from the data that our sample B has a higher mean value than deposit A. However, we don't know whether this mean value has happened just by chance through variation. So in order to answer this question, we need to formulate a formal hypothesis, and then we have to apply the appropriate statistical hypothesis test. So how do we set up this test? Well, the first thing we have to do is formulate two different hypotheses. The first one we formulate is called the Null Hypothesis, or the H0. In this example, this would be, there is no difference in the mean maximum grain size for samples obtained from deposits A and B. We then have to set up an alternative hypothesis, known as the H1. And in our example, this will be the mean maximum grain size is higher in sample B than it is in sample A. And the reason we have two different hypotheses is that we only accept that H1 is true if it is very unlikely that H0 can explain our observations. Now we have our two hypotheses, we have to select a test. Now in statistics, there's many different kinds of tests that exist, and they test different kinds of hypotheses, and they test different types of data. I've put some of the more common examples of tests on screen, and as you can see, some of them, such as the student t-test, are commonly used for parametric data, whereas the Mann-Whitney U-test is used for non-parametric data. However, in this course, we will not go into a lot of detail on these, and that's because Excel doesn't have many of these tests built in as functions. However, it's incredibly useful for you to know that these tests exist and that there are multiple kinds of tests available. A quick Google or search on the internet will show you which tests can be used for what type of data. And this brings us on to the p-value and how the p-value interacts with hypothesis testing. We've already seen that the p-value can be used to determine the likelihood of something. In the case of hypothesis testing, we use the p-value to determine the likelihood of the null hypothesis being true. So for example, if our p-value is very small, then the null hypothesis is unlikely. If the p-value is larger than our preset threshold, then it is considered likely. So the steps we have to go through while designing a hypothesis test are as follows. We specify the null and alternative hypothesis, our H0 and H1, and we choose an appropriate test. We then decide on our significance level for the p-value. As before, 0.05 is just a standard value you will see throughout science. We then calculate the value of the t-stat and the p-value. We then use the p-value to evaluate whether our null hypothesis is true or false. So if the p-value is less than or equal to our significance level, we can reject the null hypothesis in favor of our alternative hypothesis. Otherwise, we accept the null hypothesis as true and stop the test. This brings us on to something called the formal correlation hypothesis test. We've already seen that we can obtain p-values for our correlations, either using Pearson's or Spearman's rank. We can therefore formally test hypotheses that use correlation as their base by using these p-values. I'm now going to switch to Excel to carry on this example. On this Excel worksheet, you'll see two data sets in our green columns on the left-hand side here. Column A is field mark data for students, and column B is their overall year mark data. Now, I've already pre-tested this data, and it's non-parametric, which is why I've added these two extra columns, D and E. These contain our ranked data for our field marks and for our overall year marks. In this yellow section here, I've already calculated our p-values for both the Pearson's and the Spearman's tests. And the reason I've calculated both is so I can demonstrate at the end of this exercise that if you don't test your data to work out whether it's parametric or non-parametric, you can end up with a result from your formal hypothesis test that is incorrect. So let's get on and actually create our hypothesis test. In my cell here, where I've already typed in H0, I'm going to formalize what our null hypothesis is. In this case, it is that the field marks and the end of year marks are not related. This brings us on to creating our alternative hypothesis, so our H1. And in this case, I'm going to say that there is a relationship between them. There you go, with some abbreviations. So we have our hypothesis. Now we need to test it. So I've set our significance level to 0.05. Because we know the data is parametric, because I've tested it previously, we're going to use the Spearman's p-value to test our hypothesis correctly. So down here in cell I13, I'm going to actually write our formal hypothesis test. And this uses a conditional if statement. So, if J3, which is our Spearman's rank p-value, is less than or equal to our significance value, then we accept that H1 is correct. Otherwise, the null hypothesis is correct, which is G6. And press enter. This results in us being told that the field marks and the end of year marks are not related. There is no correlation between them. We have formalized our hypothesis and tested it. Now at the beginning of this, I mentioned that we also had the Pearson's p-value. Now as you can see, it is significantly smaller than the Spearman's, and that's because the data is non-parametric and the Pearson's only works with parametric data. So if we were to redo this test, but using the Pearson's value rather than the Spearman's, we get a very different result. So in this case, our logical test will be using the J2 cell, which is the Pearson's p-value, and testing that against our significance value. And again, we use the same two hypothesis cells in the same order. And if we press enter this time, you'll see that we're getting the inverse result. And this is purely down to not having selected the correct test to use when formulating our hypothesis. So now we've seen how we can formalize correlation tests, I'd like to move on to a different kind of test we can use with our data. And this is where we look at categorized data. So I'm going to change our worksheet to a new one. And as you can see, we now have some pictures of Trilobite morphology on screen. And the reason I'm putting this up is that we will be using this data to work out our categories. So just to point out that a trilobite is mostly made of a head, a thorax, and a tail. In the head, the cephalon, we have two Librogena, So these are the pointy bits on either side in purple. We have the Fixogena, which is the blue in the center, and the Gabella on the top. So just bear this in mind. Now to set up our scenario, we have this table in the top here, where we have a column of observed counts in B, and then we have 3 parts of trilobites in column A. These observed counts, you can imagine, are from a single field locality where someone has gone through the site and counted up 24 Crandidia, 32 Librigella, and 17 Pygidia, giving a total of 73 individual elements related to trilobites. This is our discrete categorized data. So what do we want to do with it? Well, the question I'm going to ask is, do the collected fossils match the expected fossils? And does our data deviate from this? If it does, can we infer some kind of taphonomic bias? For instance, current sorting. So what do I mean by expected fossils? Well, as in the previous diagram here, we know which parts an individual trilobite should have and how many of them. For instance, it should have 1 tail, 1 head, and 1 thorax. It should have 2 of the Librigella and only 1 Fixogena and 1 Gabella. So if we look at our data here, we can work out what the observed count is versus the expected count. So how do we do this? Well, we base it on a ratio. In this case, it's a ratio of 1 Crandidia to 2 Librigella to 1 Pygidia. So we take our total number and we divide it by 4. I'm using 4 because that is 1 plus 2 plus 1 from the ratio. So that's going to be our first expected number. So we expect the number of Crandidia for a total of 73 parts to be 73 divided by 4, or 18.25. Now the Librigella, we expect there to be 2 of them for every 1 Crandidia. So our expected number is our Crandidia times 2. And with the Pygidia, again, we only expect a ratio of 1. So this is the same number as the Crandidia. In order to prove that this is working, we can sum these up and we should get 73 again, which we do. So these are the expected results for a data set containing 73 individual parts. So what we need to now do is compare these numbers to our observed count to determine whether our data departs from the expected or not. So how do we test our observed counts against our expected counts in order to work out whether there's a relationship between them or not? Well, for this we use a test called the chi-squared test. And this tests the independence of our 2 data sets. Now at this point, it's well worth noting that we are now testing independence. So how far apart our 2 data sets are, compared to our previous test where we were looking at correlation, and we were interested in how close the data sets were. So this test produces a p-value that is inverse to the p-values we've been playing around with previously. And you'll see what I mean by that in a minute. But let's just calculate the p-value first. So in Excel, we use a function called the chi-squared.test. So you can start by typing in chi and you'll find all these chi-squared functions. We choose the chi-squared test. And the first thing we want to input is something Excel calls the actual range. And this is what I've been calling the observed count. So we select our data. We then have to input our expected range. And this is my expected data on this side. I can close the brackets and press enter. This then produces our p-value. So now we have our p-value, the next thing to do is formalize this test by using some hypotheses. As in previous examples, we have our H0, our null hypothesis, and our H1, our alternative hypothesis. Now for a chi-squared test, the null hypothesis is always as follows. The observed samples are independent from the expected samples. And the key word there is independent. The null hypothesis tells us that our observed count and our expected count are not dependent on each other. They are separate. The inverse is our H1 hypothesis, where we're saying that our observed samples are not independent from the expected samples. So down here, I'm going to start using a conditional if statement to run our formal test. So in this case, the logical test is, if our p-value is greater than our significance value, then we reject the null hypothesis. We instead select our H1 hypothesis, whereas if that returns false, we then accept our null hypothesis. Now this is different to our previous incarnation when we were looking at the correlation test, and this is going back to the fact that we are looking at independence this time rather than correlation. So the p-value is inversed. If I press enter, we get our result. So it's returning H1. So it's telling me that the observed samples are not independent from the expected samples. So there is a pattern here. Our observed counts are following our expected count numbers. If I was to come over here and change our values to something more extreme, say we only had one pygidia, but we ended up with 40 crandilia, we've now changed our observed count pattern to be very different to our expected count pattern. So if we come over here, you'll see that our p-value has now changed to a very, very small number. And if I bring that up with the number formatting, you can see that we are well below our 0.05 significance value. In this case, with a chi-squared test, it means we can accept our null hypothesis, which is our H0, which tells us that the observed samples are independent from the expected sample. There is no pattern between our observed counts and our expected counts. I'd just like to finish with some caveats when it comes to the chi-squared test. There's two things in particular I want to mention. The first is that you should never have any values that are less than 1 within your expected data set. It doesn't matter whether you have values less than 1 within your observed category dataset, but if you did have values less than 1 in the expected category, then the chi-squared test would fail. Another important thing to bear in mind is that no more than 1/5 of your expected categories values should be less than 5 in value. You should therefore always use if statements in Excel to test these two assumptions before you move on to actually using the chi-squared test. Otherwise, you could end up in a situation where you've done all the work and end up with a result, only to find that that result is incorrect because you have one of these two caveats in play.